Good evening. Thank you very much for finding time to join us today. But before we get into the content of today's class, I just wanted us to have a quick discussion around how we're going to work going forward. All right. So initially, based on how the semester started, the anticipation was that exams were going to start around the 15th of November. But now that we have everything happening or needing to happen before the 27th of October, right, we have had to reschedule our timelines, right? So the end result is for the next 2 weeks up until the 10th of October, we're going to be under quite some pressure. Right, but then that pressure is not going to be, we're going to be under quite some pressure to finish the syllabus, right? And then we can start revising, which is going to be questions, right? So we're going to be doing a lot of questions. So with that in mind, we've got a class today, we've got a class tomorrow. Next week, we've got 3 classes, right? So on those classes, we are going to discuss or go through the important concepts that are surrounding or what's left. So we're going to do pumping lemma today. We're going to look at, in the next class, we're going to look at Turing machines. Then we're going to look at NPDAs. Then those are the 3 major concepts that we need to look at guaranteed before the exam. Now, after that, there are some how can I put it, some topics, right? These topics, I'm going to give them to you is self-study videos, right? So I'm talking the likes of decidability and properties of context-free languages. So they are mostly theoretical. So all I'm going to do is I'm going to give you the self-study videos to go through. And then when we meet for questions, we're then going to attack a lot of those questions together. So in the next 2 weeks, we're going to look at the topics that contain the most marks. So all the machines we're going to do together. Then the theoretical parts, we're going to, I'm going to issue out self-study videos. Right. So that is how we're going to operate. Then as well, assignment 2 has been updated, right? Those who have been following have been having a discussion around one of the questions that we're going to be doing today. So there's some movement there. So by the end of today, or by the end of this week, by the end of tomorrow, we would have started on Turing machines. So I think overall, what I'm trying to say is I don't want you to panic. We are still going to finish the content. We're going to practice enough questions and sufficient for you to go and nail the exam. Right. Now, that being said, there is not enough time on your side as well. Right. So you need to start your exam prep as soon as possible. What do I mean by that? Most of if you're doing full 3rd year, you have got, I think, 27 you're writing, 28 you're writing, 2nd of November you're writing. So all your exams are clustered. Right? All your exams are clustered. So if you wait for the last minute for you to do it, right, you're going to, you may panic or you may not be able to complete everything at once. So my encouragement is, we have done PDA so far, we have done Chomsky normal form so far, right? We've done regular languages and so forth so far, right? So we have done plus or minus 30 to 40% of the content, right? So from today or after tomorrow, we've done plus or minus 45 to 50%, depending on your grasping of Turing machines. So I want you to then go and do or start doing questions and make that Telegram group active, right? Let's make the Telegram group active. Active with what? Questions of, or solutions of questions you've attempted, things that you don't understand, whatever, but as long as you have a reference point for your question, then we can make that group active. It is not only for me to respond. Discussions are allowed internally. I can moderate the discussions. You're allowed to have discussions amongst yourself. Right. So during my student days, I found that the best way I would learn was through my peers. Right. Whenever I could not understand something, whenever a peer explained it in their own understanding, it would become easier for me to understand as well. So that is the course of action that we're going to be embarking on going forward. Are there any questions? So I know there are some pending videos. I haven't checked to see if they've been updated. I'll confirm at the end of this class if they've been updated. But other than that, is there any question regarding the way you're going to be moving forward? Right. Now, I want us to look at the concept of pumping lemma. Right, pumping lemma. Right. Now, pumping lemma says, right? I think before we go into the official definition, I think it may be prudent for us to use analogies before. Right. How many of you remember proof by contradiction? Proof by contradiction. Anyone remembers proof by contradiction? All right. Do you care to explain how you understood proof by contradiction? So that's Victor, right? What do you understand when they say proof by contradiction? What is happening there? Can you explain? Okay. So when we're talking of proof by contradiction, right, we are saying you start by assuming something is true. Assume something is true. Right. Then if you go with your proof from this assumption, if you then reach a contradiction, right, so from this assumption you've reached a contradiction, what does it mean? It means that your assumption was wrong. Right? Your assumption was wrong. Right? Then if your assumption was wrong, because we have got true or false only, if your assumption that something is true was wrong, therefore it is false, then conclude false. Right. If I want to prove that x squared, let me see, so let me say 3x plus 2. If I want to prove that this is odd, prove that it is odd, for example, I would assume that it is even, right? I would assume even, right? Which would mean that 3x is even, right? And 2 is even. So we are saying if 3x plus 2 is even, then 3x is even, and 2 is even. So we know 2 is even, so we're saying 3x has to be even. Yeah. So we know this, if x is an integer, 3 multiplied by 1 is not going to be even. Then 3 plus 1 would be 5, therefore it is not that. So 3x plus 2, it is false that this is even, therefore it can be also, this is not an exact one. So I think it's, this is not going to be an exact one, but anyway, this will be, if we then find that is not even, then we then conclude that therefore the assumption that it is even is false. It is not even. Right. So that is how proof by contradiction goes in a nutshell. So if you want to prove that a language or L is a context-free grammar, is a context-free grammar. Right. So you have the burden of proof. You are given a language, you want to test whether or not it is a context-free grammar. You want to test. So the test goes like this. So you assume it is a context-free language. Then if you then go ahead with your proof and then you find that it is not, then you can conclude and say L is not a context-free language. So this is the format of the proof that we're going to use to check whether or not a given language is a context-free language. So from this format, we then see that what is missing is the chunk that we put in here, the test conditions. For us to test that something is even, definitely we know that something is even. If it is a factor of 2, it is even. Yeah. Now, let us look at what pumping lemma says now. Right, so pumping lemma with length for context-free languages can be stated as follows. Right, let L be a context-free language. What are they doing? They are assuming that the given language is context-free. Right, if a given language is context-free, there are some properties of context-free languages that we are supposed to be familiar with. If it is a context-free language, then there exists a context-free grammar for it. That should be straightforward. All context-free languages possess a context-free grammar. Right. Now we also know that all context-free grammar can be converted to Chomsky normal form. All context-free grammar can be converted to Chomsky normal form. That's straightforward as well. We have learned that. Now, if you have a context-free grammar in Chomsky normal form, say you have got S goes to X, Y, X goes to Y, Z, Y goes to A, Z goes to B. Right. These are called dead productions because they terminate, they kill. They're called dead productions. These are called live productions. They propagate the language forward. They are called live productions. Yeah. So they say if it is a context-free language, there exists a context-free grammar that can be given in Chomsky normal form with P live productions. So here we've got 2 live productions. Yeah. Now I'll explain the concept of P live productions. So if this is true, if you assume this, then this has to be true. If you have a word W that has got a length greater than 2 to the power of P, a length greater than 2 to the power of P, length of W is greater than 2 to the power of P. What is the significance of 2 to the power of P? For this CFG, 2 to the power of P is equals to 4. So for us to be able to successfully apply pumping lemma, we need a word of length greater than 4. But what is the significance of this? Right. So a word of length greater than 4 guarantees repetition of one of these live productions. So it guarantees the repetition of one of these productions, which means you have entered a loop. It guarantees at bare minimum you are already in a loop. Right. So that is the importance of 2 to the power of p in this case. So you have got 2 live productions that have got 2 non-terminals each. So 2 to the power of the number of live productions will give you at maximum the number of non-terminals you can replace without repetition. After that number, you are guaranteed to have repeated a non-terminal. Are we still together so far? Right. If you are lost, just let me know and tell me where you are lost. Now, if we have such a word of length greater than 5, there are some operations that we can do to it. That word W can be broken down into 5 parts. W can be broken down into 5 parts, which is U, V, X, Y, and Z. So it is guaranteed that if we assume a context-free language, or if we have a context-free language, we are going to have a context-free grammar for that language that can be put in Chomsky normal form, and it will have p-live productions. Now, if we are guaranteed of a word that has got a length greater than 2 to the power of p, right, that word can be broken down into 5 parts, right? Any word W of length greater than 2 to the power of p is going to be guaranteed to be broken down into 5 different parts. Right. So W is going to be equal to U, V, X, Y, and Z. Right. These 5 parts are going to be generated in such a way that the following conditions need to be met. The length of Vxy over here, the length of Vxy needs to be less than the initial word. Right? It needs to be less than 2 to the power of p. It means you can generate Vxy without going into a loop. You should be able to generate Vxy without going into the loop. So I'm going to come back and explain the other connotation of this. The length of x is greater than 0, so x cannot be now. It cannot be now. X can never be now. It has to be something except now. Then length of v plus length of y is greater than 0. Length of v plus length of y is greater than 0. This means there are 3 possible scenarios. V is greater than 0, y is greater than 0 is one of them. The next one can be v is equals to 0, y is greater than 0. The last one will be v is greater than 0, y is greater than is equals to 0. Meaning both of them can be none now, or one of them can be none now. The only restriction is that all of them cannot be now at the same time. Right. So that is the next condition. I'm going to come back now to the length of Vxy is less than or equal to 2 to the power of p. Now, that length of Vxy is less than 2 to the or equal to 2 to the power of p. It means that u and z need to be present, or they cannot be now at the same time. Because if at bare minimum Vxy is equals to 2 to the power of p, then if z is none now, or it contains one letter, then Vxyz, the length of this is going to give us something greater than 2 to the power of p. Right. So this means that, or the other interpretation of this rule is to say that both u and z cannot be now at the same time. So u can be now, z is not now, z can be now, u is not now, or both of them can be none now. All right. Are we still together so far? So Gideon, go ahead.
I just want to Yeah, that part doesn't make quite sense to me, just because it's got the less than or equal to, and as you've explained, 2 to the p is essentially the length of your word. So how would you then, if it was not less than, but it was equal, vx and y is equal to, then you can have u and z being, because there's going to be nothing left of the word, surely.
So repeat the last time. If you have u and z being what?
If vx and y is equal to the length of the word, which is also equal to 2 to the power of p, then surely the two outliers, u and z, there's going to be no letters left in the word, so they're going to be null.
Right. So remember now, the length of the word that we pick, it's mandatory for it to be greater than 2 to the power of p. Right?
Okay, I'm with you. I misread that. Yes,
being equal to 2 to the power of p, it means I have not yet reached the full length of the word w. There are still some characters missing. So those characters will need to come from either u or from z.
Yeah, 100%. That length is greater than p, so it can at most be equal to less than or equal to, but the word will always have at least one additional letter.
Exactly.
So you will have to be at least one character.
So this guarantees us that u and z cannot both be null, because they are needed. That makes sense, right?
100%.
All right, cool. Anyone else with another question? Anyone else? Right. Now, so these are the requirements for us to break down the word. These three requirements need to be met. Right. So after we break down this word into these ones, right? The choice of us breaking down the word, right, should allow that to satisfy the following condition. When we do what is called pumping, like when we increase x and y, that is, we have a loop here, we have a loop there. When we increase this side and this side, the resulting word is supposed to be in the language. So for example, if we had the language a to the power of n, b to the power of, let's have a, b to the power of n, a. Right? I can break this down. Let me explain that with the use of an example. Let me use an example. We know that a to the power of n, b to the power of n is context free, right? Why? Because we know its context free grammar is going to be equal to s goes to it's a s b, depending on where we're starting from. We can get there, and then we can put these to Chomsky normal form, right? Chomsky normal form. So it's going to be a goes to a r1, r1 goes to sb, and then we're going to have o, this goes to ab, then we're going to have a going to a, b going to b. How many live productions do we have? 1, 2, 3. So we've got p is equals to 3. Right, so 2 to the power of 3 will give us 8. So we need a word that is a minimum length of 9 for us to be guaranteed that this is going to work. Right. So what you see is that you can start loops. You're going to start looping long before you get to 8-letter words. Right. But the mathematical guarantee comes after 2 to the power of p. Right. So now they say we need to break this down. We need to choose a word, W. So let's call it A to the power of K, B to the power of K, where I can say K is equals to 2 to the power of P. Right. So this is a long enough word because this is 2 to the power of P, this is 2 to the power of P. So the length of W in this case is going to be given by length of W is going to be 2 to the power of P plus 2 to the power of P. It will be equals to 2 to the power of P plus 1. So it's long enough. Now, we now need to break this word down into 5 substrings. So we want to have U, V, X, Y, and Z. And I'm going to need your help here. I'm going to need your help. Right. What can be the most probable X? Right? The most probable X would be, I can say, I can have it as A to the power of K minus what can we say? K minus A, B to the power of K minus A. Which means for us to get to K, we need an A to the power of A, and then we also need, so this needs to be equal, A to the power of A, or B to the power of A here. Right. So this might not make sense yet, so let's do it a little bit differently. Right. So X cannot be now, right? So X has to be something. Also, X does not increase when we pump. X remains constant, right? If you look at the pumping, X is not pumped. So because when we pump, we're going to have U, V to the power of N, X, Y to the power of N, Z. So X does not increase. So X is something that needs to be stable. Let's say AB, right? So if we make this AB, it means we now have A to the power of K minus 1 A's, and we now have B to the power of K minus 1 A's. One of these B goes here, we've got A, B to the power of K, and so forth. Right. So we need to further break this down because the first condition is length of Vxy needs to be less than or equal to 2 to the power of P. So I can make this one over here A, I can make this one over here B. So it means over here we have A to the power of K minus 2, and over here we have B to the power of K minus 2. The other two B's have been used up, the other two A's have been used up. Right. So we have broken this into 5 substrings. The length of Vxy, as you can see, is less than 8, it is equals to 4. Right? Length of V and length of Y is greater than 0. Length of X is also greater than 0. So all the conditions have been satisfied. Now, pumping means we are now going to increase this. So we are going to have A to the power of K minus 2. And then if we pump this one, so we're going to have AA. And then this remains constant. Then we're going to have BB. And then this remains constant. This means that if we count the number of B's, we are now going to have A to the power of K plus 1, B to the power of K plus 1. So minus 2 plus 2 plus 1, K plus 1, B minus 2 plus 2, 0 plus 1, K plus 1. So we're going to have K plus 1 like this. So if we say K plus 1 is equals to say J, we are going to have A to the power of J, B to the power of J. So we have the same word that is in the language, equal number of A's and B's. Right. So this language, we have proved definitively that it is a context free language because number one, having taken a word that is long enough, it could be broken down into 5 substrings, right? And after we broke it down into 5 substrings, the resulting word after pumping or words after pumping still belonged to the language. Therefore, we can conclusively say that it is a context-free language. Right. Now, the same proof method can be used to prove non-context-free languages. Say this is a non-context-free language. So I then say, let us look at a to the power of n, b to the power of n, a to the power of n. Try as much as you may, you cannot build a PDA for this, a DPDA for this. Right. Why? Because you're going to push this into stack, and then you're going to pop this from the stack. You don't have anything to keep track of that. Right. So you cannot generate a CFG for this as well. But for argument's sake, we are going to say, assume L is a context-free language. Assume L is context-free language. Right? What does it mean? Then there exists what is in existence? A CFG in Chomsky normal form with P-live productions. Right. Then if we have, so we want to assume W is an element of the language and it is long enough, that is the length of W is greater than 2 to the power of P, then W can be broken down into 5 substrings. Can be broken down into 5 substrings. Right? That is W is equals to U, V, X, Y, and Z, such that, right, length of X is greater than 0. It's greater than 0. Length of X plus length of Y plus length of Y is greater than 0. So length of V plus length of Y is greater than 0. And then lastly, length of Vxy is less than or equal to 2 to the power of P. So these are the conditions, right? Right. And all words, this is the test conditions, all words U, V, N, X, Y, N, Z are elements of the language. Yeah. So if we assume it is context-free, then all this needs to be true. So now we need to test whether this holds. Right. So now our language of choice, the first thing that we need to do is to choose a long enough word. Right. Choose a long enough word. Yeah. So, like I did the last time, I'm going to choose A to the power of K, B to the power of K, A to the power of K, where K is equal to 2 to the power of P. So already you are guaranteed that this K is long enough. So don't you then go and say A to the power of 100, B to the power of 100, A to the power of 100. No one has told you that this is long enough because you cannot actually generate, or you don't have visibility of the CFG that generates it. So don't pick a number and say, I think this is going to be long enough. So use arbitraries, right? Now, from here, we want the possible allocations for, so possible allocations possible allocations for u, v, x, y, and z. Right. Before we do that, I want to then engage you on something that is critical. So we want to allocate u, v, x, y, and z, right? Now, do you agree with me? Do you agree with me that if we cannot find a possible allocation for v, or let's use x, if we cannot find a possible allocation for x, then we cannot find a possible allocation for u, v, x, y, z. We cannot find possible allocations for the other four. For us to find, if I take you back to this question, for us to be, if we are going to find an allocation for all five, it means we need an allocation for one. I don't know if that part is making sense. For you to be able to allocate for the whole five, you need to find possible options for each one, right? You need each and every one of the five to have an allocation, right? You need each and every one of them to have an allocation. Is that clear for now? Is that understandable? Questions there? Right. So what this then means is that, number one, if we cannot get a possible allocation, right? So Anthony, you're saying if we can prove that one of them, most likely x, is no, so, right. So this came in from Anthony, so you only send it to me. So we are saying that if we can prove that one of them, most likely x, is no allocations, then you're good. Yes, that's what I'm saying. So the whole pumping lemma is then, or what we're trying to do is to say, if we don't find a possible allocation or a possible allocation for u, v, x, y, and z, it then means that our assumption that the language is context-free was wrong, therefore it is not. But then now, how do we go about proving that there is no possible allocation for u, v, x, y, and z? You pick a letter, any of these ones, right? If you can exhaustively prove that there is no possible allocation of z, that will lead to the word being in the language after pumping. Then you have proven that the language is not context-free. In the earlier example, I proved there was a possible allocation for x that would lead to the word being in the language after pumping. I proved there was a possible allocation for v that would lead to the word being in the language after pumping. Right. So that is the same mindset we're supposed to have. So if you see most of the examples that I do, I usually go for v, right? Why? Because it has got the most restrictions, right? We've got v over here, it has got, and over here as well. So we've got three. So v or y are the ones that I go for. If you fail to find a possible allocation for v, then it means there is no possible allocation for the word w that will lead to the word being in the language after pumping. Are we together there? Because if we are together here, I guarantee you understand pumping lemma. Right. So let us look at the possible allocations for. Let us look at the possible allocations for V. What are the possible allocations for V? What are the possible allocations for V? Right. I can use an analogy here, and I can say, say you are at a buffet, right? There are 3 types of foods that are available, say food A, food B, food C, right? And you have to eat, right? If it is mandatory that you have to eat, what are the options available to you? Right? What options are available? What can you eat? What are the available? If you want to give a set of the foods that you can eat, what is the? Can you try and give me the options that are available to you? Right. So you can either eat A, right? You can eat B. You can eat C. But since it's a buffet, you can also have A with B. You can also have A with B, or A with C, or B with C. You can have A with C. You can have A with B with C. Right. So you can have any of these combinations if you so wish. Does that make sense? Right. So if you are looking at a language, if you are also looking at a language that is defined by a universal set AB, so it means every word in the language originates from AB or is a combination of AB. Right. So it means V is formulated by elements from this universal set. So what are the available options? V can contain A's only, maybe B's only. It can contain a combination of, so you can have an AB substring, or you can have a BA substring. And lastly, right, we know that V can also be now. Right, and if V is now, then Y is not going to be now. Right, are we together there? Any questions there? Right. We come back here now. So we need the possible allocations for U, V, X, Y, Z. So we can say there are there are 5 possible allocations for 5 possible allocations for V, right? That is, what are the possible allocations? We just mentioned them. V contains A's only, A's only. V contains B's only. V contains AB substring. V contains BA substring. And V is now. So some of you might be saying, why don't you say V contains ABA substring, right? An ABA substring is already catered for because it contains an AB substring, it contains a BA substring. So I'm looking for the base structures that I can do that do not have any repetition. Right. Now, there was Gideon's question, I think it was you, Gideon, from the assignment we're asking, right, do I need to prove for all 5 that they cannot, or I just need to prove for 1? Then I said, if I then come back to this buffet example, right, the fact that I did not eat A, or A is not for my liking, it does not necessarily mean I left the buffet hungry or I did not eat at all. A not agreeing with me does not mean I did not eat B. Right. So for me to live hungry without eating, it means I failed to eat A, I failed to eat B, I failed to eat C. I failed to eat A and B combined, I failed to eat B and C combined, I failed to eat A and C combined, and I failed to eat all 3 combined. Right. So that is the only time that I'm gonna leave the buffet or the dinner hungry. Right. Are we together there, Gideon? Does that make better sense?
Yeah, to some extent. I'm just still, I'm still stuck on that, on just the idea of contradiction.
Right.
And if you can prove one to be, not valid, then it should contradict the entire statement, because then it all can't be true.
Right. So let us look at these 5 cases in front of us. Let us say, right? Let us say we find out that this leads to U, V, X, Y, and Z, like that, being an element of the language. So it means there exists an allocation of V that leads to this word being an element of the language. Confirm? Yeah. Still referring to you, Gideon?
Yes. Yeah.
Right. So if one of these leads to U, V, X, Y, and Z being an element of the language, then it means that language is indeed context-free. Case in point, this one. V contained A's only, and it led to U, V, X, Y, and Z being an element of the language. Therefore, it was a regular language. I did not even go and bother to check all the other 4 cases that are available. No, I just needed one, and once I needed one, then that was it. Right. But the fact that this one refused, it does not necessarily mean that the others, or it is not a context-free language. Why? Because I only need one case. Maybe I find my last test case, V being now, will lead to the word in the language after pumping being in the language. Make sense? Gideon?
It does make sense, but for me, it's still, you've proved one not being true, and one being true. So that's, in my mind, that's contradiction. If one is true and the other is false, then there's a contradiction, in one of those 5 cases.
Right. Let me use this analogy. Right. Let me use this analogy. Let's say you have got a bunch of you're partying during the weekend, blah blah blah. Then a friend of yours leaves something at your place, and then they come, something very important. They say they left a work laptop at your place. Then they come to you and say, "Bruh, I need. Can I have your keys to your place? I need to go and collect my laptop." Then you say you're also busy. Say, okay, you give them a bunch of keys. Okay, here are my keys. Go and take your laptop. This person does not know which key opens, right? This person does not know which key opens the keyhole or the door. Right. So at what point does this person say, no, these keys are not for this door?
Yeah, no, once you've done all the cases, all the keys. Yeah.
Once you have tested all the keys and they fail to open, right? So you were given these keys assuming that they were for this door, right? Make sense?
Yeah.
Now, if you try the first key and it doesn't open, there's hope, okay? You try the second key, doesn't open. You try the third key, then it opens. Therefore, right, these keys are for this door. I stop, that's fine, right? But now if I then try, for example, I say I try number 3, it doesn't open. Number 4, it doesn't open. Number 5, it doesn't open. What is the conclusion? The assumption that these keys were for this door was wrong. That is the conclusion that I get to. That is where the contradiction lies. I was given these keys assuming that they are going to open the given door. Now I've tried all the given options, and none of them open the door. Therefore, the assumption that these keys can open this door was wrong, and I can conclude that these keys are not for this door. Does that paint a clearer picture?
Yes. Yeah, it paints a clearer picture. Yeah, it makes sense. Thanks.
Yeah, I had to dig deep for that one, eh?
You can reuse it next time.
Yeah, yeah, definitely. Right. So the rest of you does that make everything clearer for explaining the concept of pumping lemma? Right. So if we come back now to our language, so these are the keys, and then they are supposed, this is the door test, right? So let us test each case to see, for each case, is it possible that this would then be an element of the language? So case number 1, V contains A's only. So we can say, if V contains A's only, because remember we have got A to the power of K, B to the power of K, A to the power of K. If V contains A's, in fact, let me start with the easy ones. If V contains an AB substring, right? So if V contains an AB substring, it means it's going to be sitting somewhere here. So it containing an AB substring, it can be an AAAB, it can be an ABA, it can be an AABB, as long as there is an AB substring in between, right? So now what that means is, say, let's say, for example, I've got A to the power of K, let's say I've got AB, if V contains an AB substring, right? Let me write and say, after pumping, so if V contains, say it's AB, after pumping I'll have AB, right? So after pumping, the word will contain an additional AB substring. Yeah. So it will contain an additional AB substring. Right. But if you look at this language, how many AB substrings are supposed to be in this language, max? How many AB substrings are supposed to be in this language? 1. So the maximum amount of AB substrings is 1. But if AB is contained in V, it means after pumping you are going to have 2. So this is a word that is not in the language. This leads to a word not in the language. To a word not in the language. Right? So meaning, therefore, V cannot contain an AB substring. Right. So what have we done? We have tested this key and we found that it doesn't open our door. Right. Now, we can look at this. The same argument can be made for a BA substring. We've got one BA substring. If V contains BA, we are going to have one BA, two BA after pumping, and it's not a word that is going to be in the language. So at that point, we would have tested these two keys and found that they don't open using the same argument. Now let's come to these A's and B's and now. Right, if you look at B, for example, if V contains B's only, if V contains B's only, right, what argument can be made here? Right, do you see that all these A's will be under U? Right. The first clump of A's will fall under U. A's will be under U. Be under U. Right. What is the problem with that? Can anyone tell me what is the problem with that? For all these A's to fall under U. What is the problem with that? The problem is that U is not going to be pumped, correct? And since U is not going to be pumped, so we're going to have B being pumped, and then A can be pumped, these A's can be pumped by Y, for example, but these A's are going to remain constant, right? These A's will remain constant after pumping, leading to an unequal number of A's and B's. To n unequal number of A's and B's. Of A's and B's. Right. Therefore, which is a word not in the language, is a word not in the language. Therefore, V cannot contain B's only. All right. Now we are left with two. Contain A's only and contain B now. So if V contains A's only, what's going to happen? So there are two possible scenarios. Either they're coming from these A's or from that A. Either they're coming from this A or they're coming from that A. If they come from this A, right, then Y will need to be either this A's only or this B's only, because we've proven that it cannot contain a BA substring, right? So Y needs to be B's only or A's only, which means either way, one clump of either of B's or A's will remain constant after pumping. That leads to a word that is not in the language. Yeah. Then if V consists of A's from this clump, right? If V consists of these A's, then it means U will be A to the power of K, B to the power of K, meaning this will remain constant while this is pumping, leading to a word that is not in the language. Right. So that is what we are going to write down now, and then because we've proven that it cannot be either this A's or that A's, therefore V cannot be A's only. Right. So we can then say if V contains A's only, then they are either sorry. Right. So let's say if V contains, I need it to be bigger, say. There we go. Contains A's only, then they belong to the first or second clump of A's. Right? Full stop. If the first, then Y will need to be B's only, or the second clump of A's only. Second clump of A's only. Why? Because we have proved that Y cannot contain N be a substring. So you can write it down here, or you can say because if Y contains the BA substrings, after pumping there are going to be more BAs than in the word. Right. Now we are now taking over from B's only or A's only. If Y contains B's only, B's only or A's only, then one will remain constant after pumping. One will remain constant after pumping, leading to a word not in the language. Right. Then we also have the second case if the second clump of A's, what's gonna happen? Then we have, if the second clump of A's, what's gonna happen? Then B's will not be pumped, leading to a word not in the language after pumping. Right. We can then conclude, we can say, therefore, no possible allocation or V cannot contain A's only, since all words after pumping are not in the language. Right. So we've proven that the key that V contains A is only is not correct. So we're now left with the last one. We're now left with the last one. Right. So the last one is V contains, or V is now. Right. So what can we say about that? We can say that if V is now, then Y is not now. Right. Because both of them cannot be now at the same time. Right? Y will also have the 4 options listed above, which do not lead to a word in the language. Right. This therefore means that V cannot be now. What am I saying in this statement? I'm saying that if V is now, then Y is not now. That means Y, we have the 4 options. It can contain an A-B substring, it can contain a B-A substring, it can contain A's only, it can contain B's only. Right? All those we see, because V and Y have got the same behavior, all those are not going to have the desired effect of UV to the power of n x y to the power of n x y to the power of n z being an element of the language. Right. Now all of our keys have failed. Right. We then need to conclude. Right. So we're going to say since there is no possible allocation for V that leads to uv to the power of n. I don't know if the mathematics is going to work here. Nope. It's not going to work here. uv to the power of n. So let me just say the word being in the language after pumping it means that our initial assumption that L is a context-free language is wrong. We therefore conclude that L is not a context-free language. Pa, pa, pa. Right. Hit me with the questions. Where did I lose you? Where did I lose you? So that is how you do pumping lemma. The assignment one, they were very super sneaky. In the assignment one, they were very sneaky in the sense that they did not give you a language, right? So I think you can go through, if you go under additional resources or course resources, there are past exam papers, they've got past papers with pumping lemma questions. So you can use those as practice questions with the solutions there, right? I wanted to come to, I'll post also this. I think it is very prudent that I post this because we've got some cases. So this one as well. Then I did this and then we complete the proof and so forth. So I'm going to send this to you. And in the assignment, they say they gave us up, down, up. Right. Up, down, up, which means there were multiple languages embedded in there. So what I did is I took one, right? I took one where we have got a palindrome, right? So like we've got ABA or ABA, ABA. So this is to up, down, up. So this, the reverse of that, and that again. So this will be W, reverse of W, and this will be W. So I took a subset, then I used it to prove that that subset is not a context-free language. Therefore, the language as a whole is not a context-free language. Right? The language as a whole is not a context-free language. So that is what I did. I then picked this specific one, A, B to the power of N, A, B to the power of N, A, B to the power of N, A. So what you see is that this is going to be a palindrome. This is W, reverse of W, and W. And then once we do that, we are going to see that we have got any time that V is A's, if V is A's, then we're going to have more than 1, 2, 3, 4, 5, 6 A's. Right? The maximum amount of A's in this language is 6. If we choose V to be A's, we're going to have more than 6 A's. If we choose V to be B's only, it says that this B, or that B. If this B, then one of these is not going to be pumped because this can be Y, this one cannot be Y as well. If this B, this one will not be pumped. If this B, these ones will not be pumped. So it cannot be B's only. It cannot contain an AB substring because we are increasing the A's and we are increasing the AB substrings in the word. It cannot be BA substring for the same reason. And it cannot be now because if it is now, Y would be A's or B's or AB substring or BA. We use the same arguments to prove that it is not context-free. Right. So I know this one has been a long lesson, but thank you very much for sticking around. Any last questions from your side regarding pumping lemma? Any last questions from your side? Right. If you don't have questions, I have one. Is the exam going to be multiple choice like last semester, or it's going to be a structured question? Have you received confirmation? Have you received confirmation of what the exam is going to look like? So let me know so that I find the best possible way to then prepare you come the revision classes. If I can know before the 10th of October, that would be fantastic. So just take the initiative and email your lecturer to ask the structure of the exam.
I'm just looking at the guide that they provide on the structure, and it says that we'll have to log in and download the exam question paper. So and then you have to submit an answer file. So it's probably going to be structured.
Well, so you guys are lucky. So you don't want to write this exam in multiple choice. All right. Okay, thank you very much. I'll see you guys tomorrow. Enjoy the rest of your evening. Good night and goodbye.